In this video, we will look at Restricted Boltzmann Machines, RBMs. This video was produced in Korean and then translated into English. The audio was generated by AI, text-to-speech. In the last video, we looked at a Boltzmann machine. In this video, we'll look at a variant of it, the Restricted Boltzmann Machine, RBM. Let's take a brief look at the history and structure of RBM, and then take a closer look at the joint probability distribution and conditional probability distribution of RBM. As we saw in the last video, Restricted Boltzmann Machines, RBMs, are a variant of Boltzmann machines. Initially proposed under the name Harmonium by Paul Smolensky in 1986, and have been widely used since Geoffrey Hinton and collaborators applied the contrastive divergence algorithm to it in 2002. The contrastive divergence (CD) algorithm is a technique used to train energy-based models, particularly restricted Boltzmann machines. It approximates the gradient of the log likelihood function, making it computationally more efficient than traditional methods for learning these models. The learning rules of RBM are given as follows, which we will look at in detail in the following video. The structures of Boltzmann machines are as follows. The left is a model without hidden neurons, and the right is a model with hidden neurons. In Boltzmann machines, every neuron is connected to every other neuron, giving the network great expressive power. But it is computationally expensive, making it impractical for high-dimensional or large-scale problems. A restricted Boltzmann machine is restricted in terms of the connections between the visible and the hidden units. It is a two-layer neural network composed of a visible layer and a hidden layer. Each unit in the visible layer is connected to each unit in the hidden layer. The visible units are not connected to one another, and the hidden units are not connected to one another. RBMs can be used in many fields such as pattern recognition, classification, feature learning, dimensionality reduction. The usual version of an RBM is a probabilistic model for binary vectors. RBM learns a probability distribution over a set of input data and produces new data based on the learnt distribution. That is, an RBM is a type of neural network with a probabilistic generative model. Let's compute the joint probability distribution of visible and hidden units using a simple example. Let's use a simple restricted Boltzmann machine with 3 neurons in the visible layer and 2 neurons in the hidden layer. Let's assume that the parameters of this network are as follows. B is the bias for each visible neuron, and C is the bias for each hidden neuron, and W is the weights between visible and hidden neurons. As with the Boltzmann machine, the energy function is defined as follows, and the Boltzmann probability distribution is defined as follows. Let's compute the energy for the given state vectors v and h. Let the vector v input to the visible layer be 1, 0, 1. And let the vector h output from the hidden layer be 0, 1. Using this formula, we can compute the energy for given v and h as follows. This is the transpose of the vector v And this is the weight matrix W. And this is the output vector H. This is the transpose of the bias vector B. And this is the input vector V. This is the transpose of the bias vector C. And this is the output vector H. If we calculate this, we get minus 0.3. Computing the energies for all possible values of V and H in this way gives the followings. And if we calculate the exponential of negative energies, we get the following results. If we add all these values together, we get Z. Then we can use this formula to find the joint probability of V and H. Computing Z is intractable because it requires computing the sum over all possible states. Next, let's compute the marginal probability of V. To find the marginal probability of V, simply sum all the joint probabilities of V and H for all possible values of H. For example, the marginal probability that the vector V is 1, 1, 1 can be computed as follows. This is the sum of all these probabilities for all possible values of H in this box. Then it gives us a probability of 0.17. Next, let's compute the conditional probabilities. For example, let's find the probability that H1 will be 1 when V is given as 0, 0, 1. Using the formula from the previous slide, we compute the probabilities that V is 0, 0, 1 for all possible H as follows. To compute the probability that H1 is 1 here, we simply add these two values. Then it gives us a probability of 0.5987. This represents the probability that the first neuron in the hidden layer will fire when 0, 0, 1 is input to the visible layer. This conditional probability can be calculated using this formula. This formula allows us to compute this probability directly without having to compute the probabilities on the left. We will derive this formula in the next slide. Here, W.K represents the kth column vector of the matrix W. The transpose of the vector V is 0, 0, 1. And W.1 is the first column vector of matrix W. And the first element of the bias vector C is 0.3. If we calculate this, we get 0.5987. This is exactly the same as what we calculated in the table on the left. Since the restricted Boltzmann machine is symmetric, we can also compute the probability of V being equal to 1 given H. This is the backward path to reconstruct the vector V using the vector H. For example, let's find the probability that V1 will be 1 when H is given as 0, 1. Using the formula from the previous slide, we compute the probabilities that H is 0, 1 for all possible V as follows. To compute the probability that V1 is 1 here, we simply add these four values. Then it gives us a probability of 0.5744. This conditional probability can also be calculated using this formula. Here, WK dot represents the kth row vector of the matrix W. W1 dot is the first row vector of matrix W. And the vector H is 0, 1. and the first element of the bias vector B is 0.1. If we calculate this, we get 0.5744. This is also exactly the same as what we calculated in the table on the left. Next, let's derive the conditional probability formula we used in the previous slide. The energy function and Boltzmann distribution of a restricted Boltzmann machine are as follows. And the joint probability of V and H can be written like this. And the marginal probability of V can be written as follows. Therefore, the conditional probability of H given V can be written as follows. If we plug the energy into this equation, the numerator of this probability becomes like this. And since the denominator of this probability is the marginal probability of V, we can write it as follows. Here the z's cancel each other out. And since BTV is independent of H, these also cancel each other out. Then pH given V can be written as follows. Now let's express the denominator in a different way. To simplify the problem, let's assume there are only 3 neurons in the visible layer, and only 2 neurons in the hidden layer. This vector expression can be written in scalar form as follows. Since we are dealing with a binary restricted Boltzmann machine, each H is either 0 or 1. If we separate H1 and H2 from this equation, we get the following expression. This vector V1, V2, V3 is Vt, and this vector is the first column vector of the weight matrix. Let's denote this as W.1. This is the second column vector of the weight matrix, denoted as W.2. Then, this expression can be written as follows. This expression can be written as the product of 2 exponential functions as follows. Since the first factor is independent of H2, it can be moved outside this sigma notation. Then, this expression can be written as follows. Next, let's plug H being 0 and 1 into this expression. If we plug H1 being 0 into the first factor, it becomes 1. And if we plug H1 being 1, it becomes like this. Likewise, the second factor becomes like this. If we take the log and exponential of each factor, we get this expression. Then, this expression can be written as follows. Now we substitute this expression into the denominator of pH given V. And we substitute this expression into the numerator. Then, this expression can be written in the following general form. Using the product notation, we can write this as follows. This is the product of all the individual conditional probabilities. Here, the probability that HK becomes 1 when V is given can be expressed as follows. This is the sigmoid value of this expression. In the same way, the probability that Vk becomes 1 when H is given can also be derived as follows. The last expression in the right box is used to create the learning rules for the restricted Boltzmann machine in the following video. In this video, we looked at the joint probability distribution and conditional probability of restricted Boltzmann machines. In the following video, we will create learning rules for RBM and implement a simple RBM model in code.